Hi everyone and welcome. In this video we will discuss the concept of screening and screening masses, which is our second to last application in the context of non-zero temperature QCD. So to get an idea about the concept of screening, we can picture the interaction between matter particles as mediated by the exchange of excitations of the mediating fields. In this framework, the Coulomb potential is a potential that goes like inverse R, where R is the distance between the two constituent particles. And it goes like that correspondingly to the exchange of a single massless excitations. When instead we think of the exchange of a single massive excitation, then the appropriate parametric behavior of the potential is given by the Yukawa potential, where it goes as the negative exponential of mass times the distance over the distance. What is screening in this context? It is basically related to the presence of free or anyway mobile particles which are charged, and they cause a larger than the inverse power of R fall off in the leading contribution to the potential when we are thinking of the exchange of n massless field excitations. And then we can define the concept of screening length as the scale over which the equilibrated medium is sensitive to the insertion of a test charge, or equivalently as the distance at which a particle in the plasma and the test charge, an external test charge that we have inserted in the same medium, do not feel each other's presence. Now, when it comes to mechanisms for screening, we can think of quantum corrections coming from the vacuum polarization, but we can also think about the thermal screening in a plasma. And on the first slides, I've also linked for you a recent review about this subject. Now, with these two mechanisms in mind, let us think of polarization in the case of QED. Then we can imagine a pair of electron and positron which are at rest, and they are exchanging a single electric A4 photon. And we can think of the polarized charge distribution that accompanies of virtual pairs that accompanies each of these two particles. And then what happens is that at smaller distances r, we have less fluctuations contributing to the total charge, which entails a larger charge felt by the test charge. Indeed, we know that this electromagnetic coupling constant goes like logarithmically when we consider distances which are much smaller than the electron Compton wavelength. And this explains this form of the potential, which accounts for screening due to vacuum polarization effects. But today we are more interested in the screening due to the presence of a thermal plasma, like the quark gluon plasma in QCD, where the existence itself of the plasma has the effect of breaking Poincare symmetry of local interactions and also making the energies of thermally equilibrated fields discrete. And then what happens is that electric A4 gluons acquire a dBi mass. This is something that we have already mentioned in previous videos. And this dBi mass goes parametrically like G times T. And having defined that, we have a measure of the corresponding screening length as the inverse of this mass. However, there is the problem that the gauge dependence of the fields and also of the vacuum polarization in the case of QCD do lead to subtleties in the definition of the dBi mass, and part of this we have already discussed. Moreover, there is this unique feature of non-Abelian plasmas that the magnetic fields are totally unscreened and specifically subject to confining three-dimensional Yang-Mills theory. To that, we need to add that the non-perturbative interactions among magnetic or with electric gluons produce various bound states with masses going parametrically like G squared times T, what we call the confining scale, and as a consequence, various screening lengths of in-medium correlation functions. So to gain understanding about the screening in a thermal plasma, we might want to think about the free energy of a static quark-antiquark pair as a function of their distance, which is measured through Polyakov loop correlators according to the formula reported on the slide. Then the point is that the leading order term of the Polyakov-Polyakov correlator corresponds to a two-gluon exchange diagram, which yields the R dependence, the parametric R dependence for the potential of the form e to the minus twice the d by mass multiplied by R over R square, where md is the Debye screening mass, which remains defined in this way. And then for R that goes to 0, where perturbation theory becomes applicable, we have that we would predict the correlator to behave as the inverse square power of R. In fact, nevertheless, this is not the behavior where we fit our lattice correlators. On the other hand, for larger values of R, and specifically R which is larger than inverse g squared t, that is in the weak coupling limit, the physics of magnetic screening is what becomes the dominant effect, as was observed long ago in this paper. And in that context, the three-dimensional effective pure Yang-Mills theory, which is describing what's happening in that limit, suggests that at large distances, the behavior is rather parametrically for the potential, the ratio of the negative exponential of the so-called magnetic screening mass times R divided by R, which defines the so-called magnetic screening mass. However, additionally, as we have heard already, the infrared divergences lead to a complete breakdown of perturbation theory, and we can consider the gluon self-energy at order g square t to understand that. What happens is that you have a perturbative expansion for the Debye mass that contains a leading order, which we have already seen together, plus other terms. And in particular, if we focus on this term, which contains a coefficient c, we remember that the Linde problem causes the fact that c receives contributions from all orders. And this means that the perturbative definition of screening masses as pole of the gluon propagator is really of limited use due to the breakdown of perturbation theory. One can think about looking instead at the pole of the non-perturbative propagator, but even that would not be a good idea, at least not from a lattice perspective, as we would need gauge fixing, and we know that we then encounter Gribov copies when we try to do that. Then what should one do? One should, or could rather, define screening masses as inverse correlation length of Euclidean correlators. The drawback in this case is that these are not directly accessible in experiments, but still they are important, and they teach us about the relevant length scales in the quark-gluon plasma, which in turn is able to tell us what and how many are the active degrees of freedom at the various values of the temperature. In this respect, it is also important to mention that color screening is associated with dissociation as well as recombination. In particular, there is the old static picture within which screening leads to a rearrangement of the in-medium bound states, which in turn, as the temperature grows, leads to the melting of quarkonia bound states. And then relative yields of in-medium quarkonia in heavy-ion experiments, if this picture holds, would become true thermometer of the quark-gluon plasma. We would be able to tell the temperature at which the collision has taken place, and also during the evolution. This was then replaced by a more dynamical picture in which one has at the same time simultaneously dissociation and recombination effect because of the out of equilibrium dynamical nature of these experiments, which of course is something that is very hard to think of and describe from a lattice perspective because it really needs a real-time approach. And you can read more about this into at least those two references that I mentioned, and many more. To have an even clearer picture in mind about what the two pictures were considering, on the one hand, you have the legacy static picture where the heavy quarkonia really are static thermometer of the quark-gluon plasma, in the sense that after fully kinetically equilibrating the heavy quark states, one can ask about the probability of the survival of a given state in the hot environment. So whether this state survives in the hot environment or melts, and at what temperature it does melt. The modern dynamical picture instead holds that this quarkonium melting is really a dynamical process, in the sense that when one looks at these quarkonia states and the impact that non-zero temperature of the medium has on them, the medium actually acts like a sieve, and it filters out quarkonium states over time, depending on the strength of their binding. And the picture is really dynamical in the sense that it depends on time and it evolves with time while the plasma cools down. All right, and then let us think about these equal time spatial correlations, which, according to what we just said, are our best guess or way of defining screening masses and screening length. So what one actually tries to do is to look at spatial correlation of gauge invariant sources or interpolators that are averaged over Euclidean time, which is a crude generalization to the case of QCD of the QED concepts that equal time correlators of the electric field, such as in the formula given on the slide, relate to the parametric form of the potential as a function of R, through which the Debye mass can be extracted in that case. Then one generalizes this to the case of QCD and defines the screening length as the scale over which the equilibrated medium is sensitive to inserting a static source, which has the quantum numbers of what I am indicating by a calligraphic O in this formula, that then is the ingredient of the connected correlator that we actually measure. Then one can think of a classification of screening masses where J, P, and C stands for spin, parity, and charge conjugation respectively, and R is associated with a Euclidean reflection. And one can literally do spectroscopy. So calculations are carried out considering Lubbold, meson, and or baryon-like interpolators, and one gets to know about these spatial correlators, these equal time correlators. Then the first two things one wants to clarify is what are the limiting behaviors, the high temperature and the low temperature one. In high temperature, we have perturbation theory telling us that correlators can be evaluated by using quark and gluon propagators. And then what we learn about the mesonic state, if we do that, is that the large distance exponential decay is dominated by two quark lines, whose effective mass is given by the lowest Matsubara frequency that goes like pi t. And in the non-interacting limit and neglecting bare quark masses, then we have a parametric behavior such as 2 pi times t. These, of course, at leading order. And then perturbative corrections, what they do is they lift the degeneracy and they shift up this result, which you can read about in this paper. At the other edge, in the low temperature limit, which is the small beta regime, one can run or perform calculation with the strong coupling methods. And what one learns is that in the confinement phase, the lowest screening masses in each quantum number channel is close to the corresponding zero temperature particle mass of the corresponding quantum numbers, of course. And there is only significant temperature dependence when one reaches temperatures of the order of the critical one. Otherwise, when you are in neither of the two limits, you need to find the answer through numerical simulations. And in this framework, there are interesting observations to make. For example, observations about the generacy patterns. One can look at these screening masses and observe how chiral symmetry and effective axial symmetry restoration as T grows large affect the degeneracy patterns for these different equal time correlations and the corresponding masses. But let's focus on gluon and on electric and magnetic screening. Gluons, the electric and magnetic ones, can be studied by employing the symmetry of Euclidean time reflection, which in Minkowski space corresponds to the product of time reversal and charge conjugation. And then we have that magnetic or electric gluons transform in a given way under time reflection, either taking or not taking a minus sign, and the Polyakov loop transforms into its dagger. Remember the picture about the correlation of two Polyakov loops. Then the correlators can be defined that are either even or odd under this transformation. And depending on this fact, they receive contributions only from the electric or the magnetic sector. Truly, what electric and magnetic means in this case is whether we have an even or an odd property of this quantity, of these correlations under this Euclidean time reflection. Then the Polyakov loop itself can be decomposed. Each Polyakov loop in a correlation can be decomposed into C odd and C even states as well, according to the charge conjugation transformation that brings A4 into itself and a Polyakov loop into the start of Polyakov loop. And one can then consider the two different projections of the Polyakov loop. With that in mind, one finally obtains magnetic correlators and electric correlators, and these are the two formulae given on the slide. And from the exponential decay of these correlators, one defines the electric and magnetic screening masses. There are actually many similarities in what we just said with respect to the correlator of the full Polyakov loop rather than decomposed Polyakov loop. In particular, in the high temperature limit, the asymptotics are dominated by the glue mass in the three-dimensional Yang-Mills theory. And then one can also fit these correlators through the usual ansatz set that are used in the literature. Study of this kind were performed on the lattice, and on this second to last slide, I'm showing some results which are specific for screening masses as they can be extracted from correlators of Polyakov loops, which is the last part of our discussion. One can, these have been extracted at the physical QCD points, and you can look at these two plots where you either have the electric or the magnetic correlator as a function of the distance multiplied by t. In this way of plotting the screening, the correlators, one can, especially because the logarithmic scale has been chosen for the y-axis, one can read out the electric and magnetic screening masses over t from the slopes of the curves, assuming a Yukawa kind of trend. And one observes that screening masses are approximately proportional to T in this range. Note that the considered temperatures are given in the legend in both cases. All right, and compare that with the expected value for the critical temperature in this setup of the QCD physical point. And then one can also look at the continuum extrapolated values for the meson screening masses in a setup with 2+1 flavors of fermions, which in the case of this paper that I'm mentioning were simulated with staggered ISK quarks. These results are what you're going to play with in the assignment. What is important to observe here is that you have basically a plot of the screening masses corresponding to different channels in the light-light sector, light-strange sector, and strange-strange sector. And one can then plot them as a function of the temperature, as it was done in this set of 3 plots. And one can look at the horizontal lines in the low T limit, which are the masses of the corresponding bound states. And there is also a dashed line, which is diagonal, and it overlaps better with the sets of results as the temperature is made large, because that is the prediction for the free theory, where we expect a proportionality to the temperature through a factor of about 2 pi. All right, and then some more remarks about these plots. There are some difficulties in the extraction of the scalar state at light masses, this one over here, because there is a decay to 2 pi at finite lattice spacing that is allowed by unphysical contribution. This would go away if one would first do the continuum limit of the correlators and then extract the masses out of the continuum extrapolated correlators, which is not what was done in this case, because that is also non-trivial to do. Then one observes thermal modifications at lower T for the states with lower quark masses, and chiral symmetry restoration leads to the fact that the axial vector and vector are degenerate at the critical temperature or higher temperatures in the case of the sector that includes at least one strange quark. Okay, that is what I wanted to tell you about screening and the concept of screening in the framework of thermal plasma, such as the QGP, when one needs to take into account all the peculiarities of the fact that the QGP is a non-Abelian quark Gluon plasma. And yeah, it is a difficult topic, but it gives us great insight in the physics of this plasma.